Okay.
Here we go.
Okay, we're ready to begin? It's Thursday. All right. Welcome everybody to the ESS Colloquium. If we have not yet met, my name is Juliette Kreider. I'm on the faculty here in ESS, and it is my distinct pleasure to introduce one of our colleagues, Maureen Denolle, today for the colloquium talk. Maureen trained in Paris and Stanford, did a postdoc in San Diego, and worked for a while at a university near Boston before joining us in 2021, just in the heart of the pandemic. Thankfully, we emerged from that. Maureen is highly decorated. Among the many awards that she holds is an NSF Career Award, National Academy of Sciences Kavli Science Fellow, and the Richter Early Career Award from the Seismological Society of America. So Maureen is a seismologist, but she doesn't just do seismology, she's changing the way seismology is done and how it's defined. So working on new platforms, new workflows, new instruments, and new applications, and she's going to tell us something about that today. Maureen.
Thank you so much, Juliette. Really appreciate it was a great move. I really enjoy being here. And I came here starting thinking I would do subductions in science. And I'm sorry, but I will disappoint you today. We're going to talk about something very different. This is a very collaborative work. A lot of us at the UW, highlighted here are the many colleagues I'm working with on this particular topic. The underlined ones are the ones that have papers submitted from ESS and almost published, but students are contributing greatly. And their work, especially Manuel Yu, will be shown in this. What I've spent the last few years thinking about is how much of my strong interest in monitoring water resources from seismology has a connection with earthquake science. So this story today is to show you that connection and how water can shape the seismic risk, and I'm going to link environmental seismology with earthquake science. In 2011, there was this earthquake in Christchurch, a couple of earthquakes, 2010, 2011, very near site, very close to that city, alluvial fan, very, hydrologically rich region. The most damage from that earthquake, which really devastated not only Christchurch, but the country itself, with decades long of economical recovery, is the liquefaction that resulted from that earthquake. I'll contrast with a not inhabited region, the Ridgecrest region for the 2019 Ridgecrest earthquake in eastern California, also show interesting damage from that earthquake. What you see here is not necessarily the fault, it is the damage that is done in the shallow soils when they don't have any water in them. So what's interesting with the role of water in the earthquake damage is that we live in places that either dry up rapidly and over years, if not decades, but we also have places that at the same time may flood in the next winter. California is a great example of that. The southern you go, the more extreme weather and swings between floods and droughts you experience. But we just experienced that as well. December, right before June, all of you guys went in the south maybe, but we experienced a series of atmospheric rivers that generated a lot of landslides, and maybe a future seminar will talk about how we're detecting them. All of these landslides put a lot of sediments in the river, which we can also listen to, and they generated a lot of flooding downstream. And this very highly fluctuating water table is something that is quite interesting in an earthquake region. So the story today is to try to understand, in the beginnings of, understanding how water in the subsurface can control the seismic waves, and really what that tells us about the potential hazards that emerge from it. So I'll show you one of my favorite, very simple figures that one of the first papers that came out of my group back in Boston, where we started looking at how seismic velocities the speed at which the seismic waves propagate in the subsurface are changing over time. So this plot here is showing you the years, decades worth of seismic record. 2000 is when seismic networks started putting their data continuously online. So much science has come out of looking at what is not an earthquake. What you see on the blue curve here is the groundwater level in an aquifer. This is in the San Gabriel Valley aquifer. It's a maintained aquifer, urban, next to Caltech. And what is striking is the quite striking correlations between the two, or anti-correlation. It's very stunning. There's a little bit of that sinusoidal signals. What you see from California that's really interesting is you see multiple years of droughts. I got my PhDs right there, no more skiing, got stuck in the office, I graduated. Years of drought that continued, and then we have several years of intense atmospheric rivers and floods. This time series was done before the 2023 events in California, but we are seeing meters of gain in the water levels from just a single winter of multiple storms. And we see that the seismic velocities really track well these changes. And we see that everywhere. We see that at the level of soil moisture, so this is the amount of water in the pores in an unsaturated medium. We see a water table from the groundwater aquifer. This is the pore elastic response and the pore pressure from the water. We see that at all scales. This is a regional scale derived from GNSS, or geodetic measurements, of what these water storage at regional scales can be. And I've compiled most of the publications that I've found until 2024. This is a semi-log Y plot. But what you can see, this red curve, is if you say this seismic velocity change is proportional to, or minus, the groundwater level. So that would be the constant. dVV is groundwater level. Now there's a lot of variability among this scatter plot, which is due to wave sensitivities and interstation spacing, but we can explain that with simple wave physics. So on one side, I wanted to show you environmental seismology. This is a subset of what we can do, not talking about rivers yet. But from seismic waves, I'll show you we can monitor water resources in this passive way. And we can also monitor geomorphological processes such as landslides and sediment transport in the rivers. The timescale that environmental seismology may cover are minutes to decades, because we have decades of continuous record. Spatial scales go from meters to maybe hundreds of kilometers. The driving processes that we study in this domain, this subdiscipline of seismology, a lot of it is hydromechanics or hydrodynamics and soil mechanics. And the impact of the work that we tend to study is about drought, floods, and landslides. Earthquake seismology, which is more conventional, we care about earthquake shaking, and what's interesting about the place of sediments is that they amplify the waves. Earthquake damage relates to this often nonlinear response of the sediments due to strong shaking. And a lot of that rheology is quite complex for the soft sediments. And I'm comparing here the time scales and spatial scale, but the underlying processes are the same. We're still dealing with soils, it's still water, it's still physics, it's still hydromechanics, and what unifies the two is the hydromechanics response of these soils. So now I took this and I did some iteration with ChatGPT, and this slide was actually suggested by ChatGPT as I was trying to unify the theme. And I prompted, draw me a visual. It came with this. I usually find typos, hallucinations, nonsense. I would be so ashamed of showing a lot of my GPT prompts. But this is really stunning. There's a little bit of funny thing at the end that you can find the differences. But it's really impressive. It helped me actually unify this because I don't make enough time to sit down, pause, and reflect. Kids all over me. But what I think is phenomenal is we're getting to a stage that this is getting really good. That I could almost use this. Okay, the second one, it came up because it did two, is also fun. The volcano, especially. I think that's very creative. But then he got the actual vision at the bottom better. This came out of all of my proposals and many of my papers. I've been iterating. I'm uploading it, asking it to synthesize, tell me how to recraft things. So he knows a lot of me. So this is me, basically. But what's interesting is we're getting to this point where it's becoming useful, finally. Anyway, out of that, actually I don't have much AI for the rest of the talk. I'm going to show you how we measure this DVV. First, with record, what is noise? It's not noise, it's a physical wave. We call noise what is not your signal. It depends who you talk to. Like the urban seismologists like the beastquakes, If you care about earthquakes or beastquakes, sorry. It's just surface waves, but they're not really interesting, okay? Always happen at the same location. But it depends who you talk to. What I'm looking for is a wave field that tends to travel between stations in this sense that is stationary. I recall that two sensors, or one, we do this cross-correlation. That's where all of the computing goes. We cross-correlate, which is just a simple multiplication and shift. But we do that at the petascale, so it can be really expensive. And we do this over windows that can be an hour long, a day long, a minute long. It depends on the scale. And then we repeat that over and over. This hour and the next hour and the next hour. And you can come up with plots like this. Cross-correlation is two-sided. So the middle is 0 lag time. The left is going to be shifting in one way. The right will be shifting in the other way. What you see on the y-axis is years. These are decades worth of this repeated daily cross-correlation. Blue and red is up and down. This is your wiggle. And the stronger the colors will be indicating, the stronger the amplitude. So what we see here is there's something that arrives at about 20 seconds, 15 seconds, 30 seconds, about the same time over all the time. What's good about this is you infer that the seismic velocity is about the same for 20 years. That means if I have an earthquake, I forgot what that is, but I think it's the mountains above Caltech. If I have an earthquake there, and I predict the shaking, 20 years ago, it would be the same today. For strong ground motion, that's fine. But there's some really interesting thing that happened, and we can see it way later in what we call the coda waves. The ballistic wave, the first wave, the one that travels straight from A to B, tends to be the one of greatest amplitude, so it arrives first. But there's, and call that the direct wave, there's really fun and interesting signal that get emphasized as we get later in the coda. The coda waves just scatter around the material, and therefore they travel through the material over more extended time. If the material changes over time, we effectively accumulate these changes in that coda, and they become very visible. And you can see here the representation at the beginning, the black and the red overlap, but you see a shift. Black and red here are shifted. These are basically the same measurement at two different times, assuming a small change in that velocity. And the later coda wave just see a lot more shift. So this is measurable. Very hard to measure early on. Very obvious to measure later on. And it turns out that we can measure the shift, and they're about a linear term. So they increase about linearly, regardless of the shape of that perturbation. And by measuring the slope, we actually, with the assumption that things are moving in space, we can derive a change in that seismic wave speed that can be explaining these phase shifts. So that is the DV that that I showed you earlier, and the theory behind this supports that it's proportional to extensional strains or dilatational strains. And that can be explained in a nonlinear elasticity regime. And the effects, the trigger forces that can modulate that might be tectonic, magmatic, hydrologic. The water content enters here as well in two fashions. One, it's when we're above the water table, the change from air to water is going to change the suction forces that binds the grains, and so that stiffens the rock. This is your wet sand when the tide goes down versus the dried sand at the top of the beach. It gets harder, stiffer. And the second is if you're below the water table, the higher the water column, it just feels more pressure, and so you have more compression, and that's also stiffer. And so that actually changes that sense of the proportionality of wave speed to the water content. Okay, we model these the multiple triggers and phenomena that can overprint and modify the seismic velocities in this very crude way. We do often a linear superposition of term, which is inherited from the geodetic community of summation of strains. Often we say there's a hydrologic term, thermoelasticity, maybe an earthquake happened, which often model as a damage and recovery. Maybe some earth tides, barometry, we tend to sum them up. And there's ample evidence for this linear superposition being a good model, and there's many studies that use different parts of the system to explain the observations. A few of us have experimenting in coupling them. Things get complicated if you damage the rock while you change the permeability, so water drains differently. But in general, we've mostly done this linear superposition. I think this is when the fun comes in as a scientist. So I'm going to show you a few results. This is Quan-Fu Fan's paper, which got stuck about 9 months in editorial land. She was a postdoc here. She did some really great work. She worked really hard on studying Utah, which is represented with this cartoon, where we try to understand at the regional scale in this very complex, not tectonic, but hydrologic system, how to explain our observations, also decadal observation of the seismic velocity changes with different sites that tend to respond to different phenomena, temperature, subsurface moisture, and deep groundwater table. So the combination of them forms, can explain our observations. I just wanted to say that once you resolve this, it's a bit of pace, but when you resolve all of these changes in velocity and backtrack the water table, you can actually start mapping where the water fluctuations are coming from. And there's also ample evidence to see that at different scales. We did this by validating with groundwater measurements. Studies have shown that INSAR-derived changes in water table also explained seismic velocity change. And then there's a team that has a really cool natural laboratory in Lyon where they actually do a lot more sensing. They use a lot more sensors to map the heterogeneity, but also finding the same relation between water table and seismic velocities. Okay, I will just give you one example of science that can come out, what we've learned just from using seismology. Quan-Fu studied the state of Utah and all the seismic stations that were running for 20 years. And that's just an example to say, we are trying to understand hydrological processes just from seismology, as against just looking at correlations between water table and DV. So this one was interesting because we had to analyze the time at which the water table was the greatest just to explain our data. And we found that over the course of the year, the water table was the greatest upstream, up in the elevation, high elevation. And it took longer for that peak to propagate downstream, downhill, into the lower elevation sites. So this is I'm not a hydrologist, but it was interesting to use seismic data to constrain downstream flow rate, which are either from flowing or from evaporation. But we can, from all of these correlations, something we can do is actually try to understand hydrodynamics at that scale. Now I'd like to switch to something that's transitioning to more actionable science. There's a paper that came out from Shuzhen Mao in 2025 where she looked at these proxies of seismic velocities, but thinking about how they vary as a function of depth. And for that, we use the idea that higher frequencies, maybe 5 hertz, tend to sample the shallow Earth. And as we go to lower frequency, we can start sensing deeper. So in her analysis, it was a science paper, she looked at Southern California again and found approximate proxies, good ones to compare the different depth sensitivities with her. And this is a seismologist looking at kind of standard NASA-derived products, I think, for assessing droughts and water storage. And so what she was able to find is a good coincidence between high frequency being representing that shallow kind of soil moisture signal versus the deeper one being more sensitive to greater depth, deeper aquifers. And what was interesting, she actually found, look, it rained in 2023, but seismic data tells us that the deep aquifers are not recharged from that. So she was able to find kind of like a difference between what we thought the recharging was happening, but what the seismic data would actually tell us. So moving toward more intervention that we can do with seismology, we have this paper we call agro-seismology. If you remember Shibin Shi, I miss him. He was a great postdoc. He was here for a couple of years. And with him, we worked on a really fun project, Dave Montgomery in particular. And, Dave loves soils. And so we had this interesting data that came with, that was collected in order to understand the agricultural practice and whether or not seismic data will be able to tell us something about agriculture practice. So we looked at, we deployed in England an array that had in particular in mind the idea that tilling and compaction may affect the soil, and we wanted to see if seismic data was able to detect the different behavior. And for the ag people, talking about tilling is the idea of digging through the soil. If you attended Dave's talk a couple months ago, he talked a lot about this. When you till the soil, you're basically, the intent was to air the soil to bring more oxygen. And it's very practical during seeding and harvesting to be able to do that. However, it does disrupt the pore system, it disrupts the tortuosity, it disrupts the fluid pathways in a way that he has seen from soil science, but we are seeing now from seismology. What he's been promoting is this idea of regenerative agriculture, which is from his soil experience. It's actually an old practice bringing back from today, where we do composting, no-till, crop cover, and crop rotation. These are the intervention to rebuild the soil health, the pore structure that would favor a stable hydrologic system for the soils and the microbiomes. I'm going to stick in the physics sense. I don't deal with the earthworms yet. But my colleagues can listen to them with seismic data, FYI. So we worked on this fun project called AgroDAS, and Ethan Williams, who was also a postdoc here, deployed on bare soil in this agricultural center and university in England. It was cold, it was muddy and cold, March in England. But from that experience, it was very interesting to see the effect of me walking on soil and its effect on compaction, on water retention. Catherine, she's almost 4. She was tiny still. She came with me and she was totally happy on the field. They are here listening to the worms, so I don't know about that paper, but when it comes out, I will tell you. What was interesting is when we collected this fibroacoustic sensing data, we had to go on the soil, but as least disruptive as possible. But nonetheless, just walking on it, we were starting to close the pores and prevent water from infiltrating. So I could see already tractors and the compaction has a really profound effect on water penetration in soils. So the experiment we just worked on is this in Harper Adams University, only 36 hours. We deployed this DAS cable in this square fashion. This was photo done in the summer. And there was this, each plot were 3 meter wide, and they each have different treatment history for the past 12 years. So each plot was consistently treated the same way for a long time and have this nice difference in structure. The UW farm has a similar system, except that they have done it incrementally over the years. So I wanted to show you the difference in this seismic response over time. This is taking our 36 hours record. This is lag time from that correlation I showed earlier. It was two-sided. Now I'm just showing one of it. because it's a single correlation, so it's symmetric. And we're looking at relatively high frequencies, 50 hertz, so it's unusually high, I think, for a lot of seismologists. What's interesting here, you see the time, you see this lag time here is not changing, but when you see, as you go later in the coda, you see a lot more changes that happen over this course of 36 hours. Now, we're not talking about decades. We're seeing a lot of changes visibly. You can see them in the eyes. It's not this fine thing that we're going to try to find with correlation. It's just here. It's 60% of changes in velocity. 60%. Usually people report 1%, 0.1%. It's really massive. Right next to it, because agricultural scientists have an interesting way of setting up their plot. Every plot had a completely different setup. They have a different tilling depth, they have a different porosity, they have a different compaction, and there was not like, this set of plots will have a constant porosity, and we're going to vary systematically the compaction. So every plot showed extreme variability in the way they had the tilling and tilling depth, compaction, and whatnot. And so we expected extreme heterogeneity. So these are a few meters apart channels. And you can see from one set to maybe 10 meters apart, a huge difference in the way the seismic response is. Right? So we see extreme heterogeneity in just these soils. So the water budget that we're doing to explain this is the physical model. There's no AI. It's purely physical model that incorporates density changes with water, with different saturation, and section forces that depends on dynamic capillary forces. But what we have to do to explain our velocity, which I'll show on the right, is a water budget. And so in this water budget, we have rainfall coming in, which we derive from seismic noise itself, because if you hear the rain, the seismic sensors do too. But they listen to it in a way that's really high frequency, and that allows us to go within the sampling period of a MET station. We were able to get, rainfall data every seconds. So we use that seismic noise to turn that into rainfall. That's our input. In the output, we assume a downward drainage and evaporation, although it was March in England. There's still some evaporation that happened. That gives us a time history of saturation that changes in the soil. From that, we derive a change in density and in rigidity, depending on the different forces at play, suction forces or not. And from this, seismic velocities are square root of rigidity over density. And that's it. That is what we're measuring. We're going to measure seismic velocities. So we can turn this into an inversion system. We can solve for saturation to explain the seismic velocity. So this is a little bit of our model here. On the right, you see two different channels, so they have different plots associated with them. The one in the middle here is showing you this absolute velocity changing over time, and we're talking about almost doubling the velocity over time. This is just a 36 hours window. The yellow part is when it was sunny. I grew up in Brittany, sunny in March. Does not mean warm, but there's sun, and that is sufficient radiation to evaporate. We have a few rain events, again, very similar between England and France or Brittany. The rain events reduce the velocity because water started getting into the soils, and that reduced the velocity by a lot and all at once. Interesting, we also had a rainfall here, and then we have this slope here that shows a slow stiffening of the soils, which is associated with the slow drainage of the water down. Different time scales, different processes. Evaporation can be fast, drainage can be slow. What's interesting is see a short distance away, almost nothing is happening. Velocity is almost constant. So huge variability, short spatial scale by design of this agricultural field, but the saturation velocity behave very differently. So if we plot all of these time series into this tilling depth, which is a tilling intensity in some ways, and tire pressure, which is a compaction, we just plot the data. No interpretation here, except for the color scale, because you've got to put some meaning in this. You see that for little to no tilling and compaction, these time series are almost flat. Nothing is happening. A lot is happening, they would tell you. No, it is infiltrating at the right pace. That is actually a stable saturation. So water comes in. It's not like it's raining differently in different plots. But it infiltrates at the right pace to be stable. However, for increased pressure, compaction, which is you walking on the soil, you see a lot of evaporation, which is fine because as you saw the photo, if water pulls up, it's going to evaporate better, right? So if the water is very shallow, it will go up further. And or a lot of tillage, you have this interesting different kind of evaporation that I will not get into, different stages of evaporation. And then everything in between is kind of hard to understand. There's a mix of both, competing interests maybe for water retention, but still not very stable. So we're all ever hopeful. We'll hear tomorrow about this fate of this paper, but we interpreted this as a natural soil conditions where rainfall infiltrates properly, and there's this natural equilibrium of saturation in the pores that's very stable. The root systems are undisrupted, fungus is there, and then you go to Dave for the rest of that story. But what's interesting for the disturbed soil is we had to understand, as seismologists, what a plow pen is. It's the effect of plowing is basically creating this layer that stops water from draining down, so water just pools above, and it therefore is more able to evaporate, but also prevents water from penetrating down. So it's a complete disruption of the fluid pathways due to plowing and compaction, but seen from seismology. So how does that earthquake, where did the earthquake comes into this picture? So now I want to turn into this connection with earthquake science. We all know this, the National Seismic Hazard Map that was issued in the latest one in 2023, which shows that the greatest hazard is proximity to faults or to potentially greater ground motion, depending on the earthquake occurrence and our knowledge of how waves propagate from source to people or to site. What I'd like to bring to this picture is that we also know that the state of rainfall, extreme rainfall, and drought has a map, but it's not stationary. This map is stationary except for the occurrence of earthquakes. This one is going to change every day, depending on the rainfall, depending on the projection. And there's this combination of both that I find fascinating. In fact, the recent USGS adoption of this ground failure metric, which combines liquefaction and landslides, again, different phenomena, similar processes still in the soil, are rooted in ground motion strength and material wetness is one of these parameters. And there's more parameters about proximity to rivers, to land body, water table, saturation. These are just parameters plugged in that are not time varying, but they're used to assess the susceptibility of landslide and liquefaction. And this is a piece that can be time dependent. The coasts are sinking. This is seen that from surface elevation, that there's parts on the coast that are inhabited, close to faults, and they're sinking on top of a potential sea level rise, with changing in flood hazard in some region. And Alex Green, who's a grad student at UW and still here, estimated that this change of liquefaction potential that would rise with the sea level. So more elevated groundwater table means potentially more liquefaction. And so this is what we're starting to do here. And this combination of environmental seismology with Manuela, wave field physics with EU, these are AI models, and Morgan Sanger and she looks at high spatial resolution of geotechnical data and its conversion to liquefaction potential. So these together, it's a dream team, by the way, of grad students. We're going to combine this and understand whether or not a varying water table is going to affect it. And Ian Stone was here. We talk about what could be a fun case And Nisqually is going to be one of our target of validation to think about what happened in Nisqually in 2001 and think about what's going to happen in the future. Thank you for your simulations. So we're marching toward my dream of a digital twin for thinking about this system-level science. And we got funded by the College to the Crest. We call it the Gaia Has Lab. Scott is developing all of our awesome tools and our data platform. But you can join us in 375 at 1:30 p.m. every week on Thursdays. We tend to have donuts and chocolate and coffee, and we talk about this idea that climate can have compounding effects on geohazards with our targets of liquefaction, landslides, and floods. Shout out to Scott Magician, who put together this image that is not profound scientifically, but so interesting to see. This map is, Mount Rainier. You potentially recognize that. But the background is soil depth, and you can see what the seismometers and the river gauges are. And that, to me, is just a non-scientific, but a visualization of what our team is trying to do, is understanding this water system, the soil, and the seismic hazard. So it's just in the work, but I think it's going to be a really cool project. So I conclude here. Hydrological state can control the seismic behavior, great for monitoring resources, but may have an effect on the hazards. I really like this link between environmental and earthquake science to probe the system at different scales. And in the work, we have a lot of physics grounding, sensing plus AI acceleration, that is going to help us understand and predict the hazards with an S. Voilà, thank you.
All right, if you'd like to ask a question of Marina, I'll bring you the microphone.
Hi, Maureen. Thank you for your talk. For those of us who work outside of the observational record, in like deep time archives, before any sort of sensor was dreamed of or deployed, or people who work strictly in the historical record, also before the advent of sensors, how can the coupling that you're talking about between the hydrological and earthquake cycles help us think differently about the records that we are using?
Yeah, thank you very much. I think it has been a necessary condition to interpret the record to understand the hydrological state and the hazard. I'm not familiar with the literature that much, and I should, but there's a strength at UW that try to understand hydrological state, landslide hazard, and liquefaction to look at sediment record to try to tease out which ones are causing the variations. So it has become maybe a necessary step to deciphering which one is controlling it. I don't have an answer beyond that, sorry.
I'll just shout. Do you have an idea of how transportable the results are? Say from your studies in England, can you use those to predict what something in Colorado might look like?
Yes. This is where a lot of the observational record, especially for near-surface observation, is extremely site-specific, and it's difficult. It's because the geology varies at such a short length scale. It's quite difficult to generalize this phenomena. And so we've maybe an obvious answer, and I apologize for that, but it's really trying to understand what physical model we can use to explain it. And the parameters that will be used for tuning the physical model might be more related to the processes, the type of soil, the tilling depth, the land management. These are the parameters that we hope would be indicator of the hydromechanical state, which is our basis for generalization. But part of our effort in combining for this data platform is we want to understand these drivers to the physical state so then we can generalize in other places. hopefully.
So kind of like in response to like that previous question about how if you can like extrapolate it, and you said no, it's very site specific, and like you kind of need to like develop those models further. With it being site specific, does that mean like you'll have to, if you want to kind of make these models for, you know, farms that exist in other locations, basically with different soil conditions, different land management, does that mean you're gonna have to like set up these sensors every time? And if so, is that gonna be like a cost barrier for any like agriculturalists who want to try and use this system to be more sustainable?
Yes, we so a little bit on that, transforming this to be more at the scale of a farm. These are the box that interrogates, that sends the signal for this fiber is a bit expensive right now, but prices are going down. The cable itself is very cheap. And what's attractive about it is that it's centralized, which means there's one battery for that interrogator. The cable, you didn't see the sensors actually on this photo. These are the sensors, extremely minimal footprint. And actually these ones are above ground, they're just held on by mud in some occasion, coupled. Because it's such a small footprint, it does not disrupt the mechanical property where we put the sensors. So it's easier to maintain. It's a little bit expensive at the beginning, easier to maintain, but it has the benefits that for regenerative agriculture, reviewers were asking, like, can you scale this up to the farm? And the idea for regenerative agriculture is you cover, crop and cover, and you actually don't till. And so in some ways, there might be a few years for seeding to be a little bit tricky, but it ends up buried over time, and so that becomes permanent. It's eventually going to become a more cost-effective. Nowadays in ag tech, they have to put sensors in the ground to get the right scales and the right temporal resolution. And these come at cost. There's telemetry that's a little bit tricky, but there's also not the spatial resolution that you might hope with this system. Or you can use remote sensing, but they still have meters to tens of meters or 30 meters of spatial resolution, which is pretty fine, but the temporal resolution is not there to do this, to probe the rapid dynamics that we get from a single rainfall event. So we hope that this will be attractive for future efforts to fund and test and deploy and go on.
Thanks, Maureen. I'm wondering if you've thought about, and I'm sure you have, and maybe you can answer why this is or isn't a good idea, integrating some of these tools and the work that you're doing with like these observations like soil moisture from satellites or gravity data from GRACE or other things like that. Like, is there a way to integrate your work with that work to sort of look across scales?
Yes. So actually this is an INSAR measurement. We are going to, they have different sensitivities. Now I can go back to this one, where they're going to show you the different sensitivities of the satellite measurements. The hope that we have with Gaia is that we're going to co-locate our ground-based sensors with satellite measurement to try to understand. And then it becomes, maybe we don't have a deterministic way to combine the sensor data, but we can fuse the data for a better outcome. Like, it's actually easy to craft an objective problem and solve for it in this deep, neural network way. But doing sensor fusion or data fusion in order to meet the outcome, which might be, seismic velocities at super resolution in space and time, is something that is possible and love to do. A lot of this is so much about intersection of domains, disciplinary domains, plus sensor that have multiple modalities. Geospatial is going to be great at spatial resolution, but it's every couple of days or cloudy sometimes. And then the ground-based sensors are sparse, but it's every second. And so the opportunity is in this combination.
Yeah, thanks.
And the geology. We got to look at these rocks. Is water flowing on top or? So I think that's going to be the context layer in the tech jargon. The context layer, the geological rocks, will be important.
More questions? All right, pushing us in new directions. Thanks, Maureen. Let's give her a round of applause.
Thank you so much.
And the great news is that she's here among us, so we can ask questions anytime.
Yes. 204 ATG, or coffee is 375. Johnson.